Hi, last time we looked at this professional decade resistance box and I thought, well, why not check out my old one that I built when I was a kid, this do-it-yourself one. Could be interesting. Let's go. Haven't opened it for a long time. Hey. Now, I've got no recollection of exactly when I made this. I might have been, I don't know, 12 years old or something. I was very young when I actually built this. It was one of my, it was a big thing I wanted to build back then. And, it wasn't cheap to buy these knobs and these, the switches weren't that expensive. They were just standard PCB mount ones, I think, from memory. They might have been the lug terminal type. Yeah, they're probably the lug terminal type. Well, I don't know. I haven't opened this literally since I built the thing, I don't think. And it's gone a bit dicky. Now, it's a 6-decade unit. It only goes from 10 ohms up to 10 meg, but that's a pretty darn usable range. And I didn't go to 7 because, well, 7 was like an odd one out, and it was just much nicer to have the 6 decades in this one size Jiffy box, which is an off-the-shelf Jiffy box you could get back then, and you can still get now, Australian made Jiffy box. If you don't know about those, it's a very Australian thing, and you can probably see that the rust on the screws. It's just it's terrible. Anyway, let's but before we crack it open, I might do a quick check again. But as I said, it's been a bit dicky lately, and that's the problem with these things. The contacts in the switches just go dodgy after a long period of time. Now, as you can see, it might seem all nice and stable up here. I've got it set to 10K on my times 1K thing here, and it's not too bad at all. You dial it down, 9K, okay, not a problem, 7, 6, hey, there we go. We're getting a bit dodgy. There's something really going on with that switch. And 3, 2, and yeah, look at that. It's all over the shop. Whoop. And of course, if I put it down to 0, that's supposed to be 0 ohms. I've dialed 0 into my box, and well, as you can see, it's like all over the shop there. So there's something at least wrong with that switch, maybe a couple of the other switches as well. So it's only happened fairly recently. It was working reasonably quite well, but yeah, like I said, this thing is probably 20, 30 years old, something like that. So it really is quite ancient. It probably needs an overhaul, but now I've got this new IET one. I guess I don't need it, but it'd be nice to have a second resistance box, so I need to overhaul this sucker. But let's crack it open and see what's inside, because I completely forget what it looks like. And I think it's quite appropriate that I use the exact same screwdriver I almost certainly used to assemble this thing. This is my Phillips that I've had since I was knee-high to a grasshopper, and let's open this sucker up. I've had this screwdriver since I was a kid, and I've lost it quite a few times over the years, but it always seems to come back, just like Indiana Jones's hat, It's something magical about this screwdriver, and it seems to fit absolutely everything that I've ever done. And it was my screwdriver I loved to use as a kid, and I almost certainly, I don't actually recall putting it together with this, but I pretty much guarantee you this is probably the one I use. So let's, crack this thing open. Hey, there we go. There we go. Ta-da! And there it is. Woo! After all that time, the magic smoke has just escaped. I've opened it. And of course, there it is. Made in Australia. You beauty. And in this case, it is actually a 10 resistor box. So it does actually go from, as you can see, 0 to 10. So you can actually dial it around, and 10 is going to be the same as the next one up. But you don't need to do that. You can just go from 0 to 9, which is fine, because then if you want to go to 10, then you just go up to the next decade. Not a problem. And as you can see, I've got them going like this. 10 ohms, 100, 1K, 10K, and 100K and 1 meg. And of course, they don't actually go in that sequence under the bottom, or they don't have to. It starts out at 10 and then it jumps to the 100, but then it jumps over to the 10k here, and then it jumps over to the 1 meg and back to the 100k and then over to the 1k and through. So it doesn't matter because they're in series. It makes no difference whatsoever. Now, if you've got a keen eye, you'll notice that these two switches over here are different to these four. These four here are the PCB type. They don't have the solder eyelet tag like these ones here do. So I must have had, like, maybe I had these four in my junk box or something, or I had these two, you know, or these two, and I had to go out and buy four more, and maybe the local Dick Smith didn't have, you know, a particular type. Maybe they only had four of these and I had to get two different types. But yeah, they are the cheap Dick Smith switches, which is no surprise in, which would have been Asian sourced at the time, of course, you know, from the cheapest supplier as they did, and they would have changed suppliers every week. So, you know, the quality of these switches is quite poor. So it's no wonder, like, you know, 25 odd years later or something, that it's just, you know, it's just gone to the dogs, really. So that's, you know, let that be a lesson to you. You use these cheap quality switches and it works perfect the first time you build it, but yep, down the track, sooner or later, you're going to come a gutser. Now, of course, if you want to make one of these, it's not rocket science at all. It's one of the most simplest implementations. A basic decade resistance box, as you saw in my one here, is just, mine's a 6 decade. So the first decade, you've just got, well, as I said, I had actually 0 to 10, but you don't actually need that. You only need a 10. So mine uses an 11 position switch to get from 0 to 10, but you can use a 10 position switch from 0 to 9, and that's good enough. And you might start out at 10 ohms as I did, and the next decade you go up to 100 ohms, and that's how you wire it on. Very, very simple. And they're just wired in series in a cascade configuration like that for as many decades. And there's your binding posts there and there. Not a problem. That's your standard basic decade resistance box. Now, of course, you can do that using either standard traditional rotary switches like this, and these knobs actually can be rather expensive. They could be the most expensive part of the whole thing. Just make sure you use good quality rotary switches, or you can use thumb wheel switches as IET have done in this box. And a EEV blog forum user by the name of VTI, he actually made one using some cheap Chinese you know, one hung low brand ones off eBay, and this is what it looks like. It's quite nice. It's quite compact. You know, make it into a little box, custom front, you know, a square front panel cutout for it, couple of binding posts, and Bob's your uncle. You've got a neat little decade resistance box. But if you, once again, if you use these cheap switches, don't expect it to last for, you know, 5 years or a decade or something like that. It's very likely to be quite a bit dicky down the track. Now, when you're designing a decade resistance box like this, it's important to understand tolerances and temperature coefficient. Now, a lot of beginners make this mistake that if they think that they put all these resistors in series like this, then the percentages, let's say you've got a 100 ohm resistor at plus minus 1%. They think that if you put them all in series like this, then the percentages will add up. So in this case, you've got four 100 ohm resistors in series, and you'll end up with a 400 ohm resistor plus minus 4%, or some, you know, some weird combination of that. Well, it's not the case. You will end up, regardless of how many resistors you put in series, you will end up, the final resistance value will still be plus minus 1%. And if you don't believe me, let's do some simple math and check it. Now, a 100 ohm resistor plus minus 1% means it can have a value from 101 ohms to 99 ohms, anywhere within that range. Technically, it can be any value there. So let's take the case of that. They're all, in this case, we've got four resistors. They're all 101 ohms. What do you end up with in total? In that case, you get a total resistance of 404 ohms. And how much is our value out at 400 ohms? Well, it's out by 4 ohms. So if you do 4 divided by 400, because that's 400 is the nominal value, times 100, you get 1%. Bingo. And if you do the same math with all the, with 100 resistors in series, it doesn't matter. You're still going to end up with a total tolerance of plus minus 1%. So if you use plus minus 1% resistors in your decade box, you can say your total your total resistance box tolerance is plus minus 1%, just like the IET Labs one here. It uses 0.1% resistors in it, and they have no problem saying the accuracy is plus minus 0.1%. Now, one of the things they don't tell you on this box is the temperature coefficient. I actually asked EIT and they said they use 25 ppm resistors, as I mentioned right at the start, but they don't actually mention that. And that's, if you're designing a precision decade resistor box, it's important to take that into account. Well, what does 25 ppm means? Well, it means that 100 ohm resistor, or whatever resistor in the box, will change 25 parts in the million per change in degrees Celsius. And what's 25 parts per million in percentage? Well, you can simply convert those. They're completely equivalent. It's 0.0025% per degree C. Now, you might think, hey, that's nothing. That's half a bee's dick. It's tiny. Why do I need to worry about that? I'm only going to use this box, this decade resistance box in the lab, and the lab's going to be, 20 degrees plus minus 5. What's the big deal, at all? It's not going to change that much. And that's true, right? If it's only 0.0025% per degrees Celsius, and, your lab might change, if it's air conditioned, it might only change a couple of degrees or something like that. And really, when your resistors are if you're using a 0.1% resistor, as you are in this case, or even a 1%, well, what does it matter? What you're forgetting is that the resistors inside these boxes, they will heat up. They can actually heat up above the ambient temperature depending on the current that you've got flowing through it. I squared R, basic stuff. So let's have a look in the case of this particular box here. I don't know the exact resistor used in there because they're custom, but we can get a generic resistor, a half-watt resistor. It's pretty much going to have the same thermal resistance for basically any any same size half-watt resistor. It's going to be very similar. So I'll take a generic Vishay brand resistor here, and this is the particular model that is half a watt, sorry. And you've got a thermal resistance graph here of the power dissipated in the resistor and the heat rise above ambient, which is important, which we'll look at later. Above ambient, that the temperature will rise when you dissipate half a watt. So you can't just magically, make this thing, put enough voltage in here and make it dissipate half a watt and not expect its temperature to go up, because it will. Okay, and if you take a look at the graph down here, it is, this is the line here for our particular size resistor. They do come in different body sizes, but this is the one that's rated for half a watt. And you'll see if you go across here, well, there it is, half a watt goes up there, and it's around about 60 degrees Celsius. So it's going to rise 60 degrees Celsius above ambient temperature when you dissipate its maximum power rating of half a watt. Crazy. So now we know that if we dissipate 0.5 watts into one of those resistors, then it's going to rise 60 degrees C above ambient. But because we're comparing it to the ambient temperature, we'll only take a delta T of 60 degrees Celsius. But the temperature of the resistor actually gets to 80 degrees Celsius if you've got a 20 degrees C ambient temperature. So let's look at what percentage change. Remember, it's 0.0025% per degree C, which didn't sound like much, but if you take 0.0025% and you multiply it by the 60 degrees Celsius change, bingo, that gives you a value of 0.15%. And if you're using 0.1% tolerance resistors, nominal, then bingo, you've already exceeded that value by another 0.05%. It's not going to matter maybe if you use a 1% tolerance resistor or something like that, but if you're trying to design a decade precision resistor box like this one with 0.1% resistors in it, that can really matter. And of course, not to mention the stress you're going to put on the resistors, and you can change their life based on if you operate them at a higher temperature. And correspondingly, if you don't have to have 0.5 watts either, if you're dissipating 0.1, it's going to be 1/10 of that value, because as you saw on the graph here, it's a linear response, completely linear, so that even if you're dissipating a very small amount of power, it still can rise by 5 or 10 degrees, not a problem at all. So you've got to take that into account. And if we come back to our data sheet here, these high temperatures, you don't want to be running resistors continuously at high temperatures like that, because this is the one we're looking at here, okay, to keep its plus minus 0.15% over the maximum typical variation in the resistance over the load life, the load life shift versus power rating table we've got here. We'll see that resistor, if it's half watt dissipation, which was what it's actually rated at over its life, it's going to be plus minus 1%, not plus minus 0.1%. So just remember that, and that's a power rating at plus 70 degrees Celsius. Now, the other way you can make a decade resistance box is by using 4 individual switches like this, just single pole, single throw switches, either slide or toggle or whatever, or dip switch or whatever, per decade instead of a rotary switch. And you only need 4 resistors like this per decade in the 1, 2, 3, 4 sequence like this. No complicated switch arrangement, but instead of dialing the exact value onto the unit itself, you have to actually do a bit of math and add it up. So in this decade, here, if you want to, say, have 7 ohms, for example, or 70 ohms in this case, because it's a 10 ohm decade thing, then all of the switches by default are closed, okay? In this whole sequence here, they're all normally closed. And if you want to, say, do 70 ohms, you would open switch 4 and open switch 3, and it puts 40 ohms and 30 ohms in series. And you can get any value, in this case, from 10 ohms up to 100 ohms per decade. So you do actually get, like the 11-way switch we actually looked at before on my particular box, you can actually dial anywhere from 0 up to 10 on each decade, and you put them in series. And of course 10 ohms is 10 is a standard E12 value, and 20 and 30 are E24 values, and of course 40 ohms is or 40 is not possible, or 400 or 4K or whatever is not possible in any of the standard E ranges, but you've already got your 20, 200, etc. So you just put 2 of those in series to use your 4-1. Or likewise with the 300, you don't need a 300 value. You could use 2 150s in series if you wanted to, using the E12 range. But there you go. That's just another method of doing a decade resistance box, except it's a bit trickier in that you've just got to add up the particular values, and it's a bit confusing that the switches have to be normally closed. And one of the things with the normally closed switches, one of the problems with this configuration, instead of having just 1 switch contact resistance per decade, you've actually got 4. So if these are all normally closed, you've got those 4 contact resistances there. So, if you're doing a box like this, you might start out with a lowest first decade of only 10 ohms, as I've shown here. You might not want to go down to the 1 ohm range, and certainly not down to the 0.1 ohm range, but you can if you want to, if you're using high quality switches, etc. But just something to consider. So that's another way to do it. But they all work the same. They all put resistors in series for a decade. That's all it is. So go build yourself a handy decade resistance box. They're a great fun little project, and you'll be surprised at the uses that you'll get out of the thing. It's amazing. Catch you next time. Don't forget to subscribe, rate, thumbs up, like, all that sort of stuff. I'm on Twitter as well, EEV blog. I tweet a lot. do all sorts of stuff like that. Subscribe to my YouTube channel, you get the videos first. So many things. Join the EV Blog forum. Everyone discusses all my videos and has fun hanging out on there, so go join them. Catch you next time.